Due to a current through a circular loop. In the previous case, we have already discussed how the magnetic field lines look like in the case of a straight current carrying conductor. But in this case, our conductor is in the shape of a circular wire, a circular loop. Okay. So in this case, what will be our observations? The magnetic field lines produced by a straight current carrying wire depends inversely on the distance from it. Right, we have discussed that as we were moving away from the wire, our concentric circles were becoming larger and larger, the deflection in the compass was less, and we concluded that as we are moving away, the field is decreasing, the circles are becoming larger and larger. So, there is an inverse relation. Similarly, at every point in a current carrying circular loop, the concentric circle represents the magnetic field around it would become larger and larger as we move away from the wire. Before going into the detail, let us see how the circular loop looks like. Suppose this is a circular loop. Okay, it is like this, right? As if I have taken the wire, I have made a circle out of it, and the current, it started flowing in the, let's say, anti-clockwise direction. What is this? Anti-clockwise direction, right? Now see, it is very important that you understand the plane of the wire, because if you understand the plane of the wire, you will be able to understand how will the shape of the magnetic field lines be. Suppose in this case, the plane of the wire is the plane of this board or the plane of your paper on which you are drawing. Okay, so this is the plane of the wire on the board, as if I have kept the wire on the board. Okay, I will show you with the help of a real time example. In this case, the wire, imagine the wire is kept on the board. This is the plane of the wire when it is, the plane of the wire is matching with the plane of the board. But if I keep the wire like this, the plane of the wire has become perpendicular. In both the case, you will see a shift in the magnetic field lines. In this case, we will draw the magnetic field line first, and in the second case, we will take the plane of the wire perpendicular to the plane of this board. Okay. So, in the NCERT, the diagram that you see is basically when the wire is perpendicular. See this diagram. In this case, the wire is kept like this, right? You can only see the front part. The back part is not visible to you because it is perpendicular. But in this case, the entire wire is visible to you because we have kept it like this. Now, in this case, how will be the magnetic field lines? Just take every wire point. This is a circular wire, right? Now, if you want to draw the magnetic field line, you only have to use the right hand thumb rule. But how will you apply it over here? In this case, take each segment of the wire. Each segment of a circular wire will be like a straight wire, right? Suppose I take this segment only, right? What is happening in this segment? Put your thumb in the direction of the wire, in the direction of the current, and close your finger. So, the field lines are going in, coming out, going in, coming out. So, how will the field lines be? They will be the concentric circle. This will be the shape. Over here, if you look, how is the current? Current is going down. I have to put my thumb like this. And how are the field lines now? They are going in, coming out. Going in, coming out. And in the form of concentric circles, again wire at the center. Right? This is the shape. How will be the direction? Inside, going in, and from here they are coming out. Over here also, see, going in, they are going in and coming out. right? These are your magnetic field lines in the case of circular wire when the plane of the wire is this board or a table, okay? And the field lines that you are seeing, they are perpendicular, right? They are perpendicular. They are like this. They are going in, coming out, going in, coming out. This is the plane of the magnetic field, okay? The concentric circle representing the magnetic field around it would become larger and larger as we move away from the wire. Look at the concentric loop. When you were closer to the wire, it was a smaller circle. As you moved away, the circle increased. After a point of time, somewhere in the center of the wire, there would be a point where you will see only the straight line, because if you make circle, they would intersect, right? So at somewhere in the middle, these circles will act like a arc, like a straight line, okay? Because they are widening up, they are opening up. So I hope this is understood. If we keep the plane of the wire, this is how blue lines, they represent your magnetic field. These are your magnetic field lines. Now, by the time we reach at the center of the circular loop, the arcs of these big circles would appear as a straight line. See, what is the meaning of this? This was my circular loop, right? The magnetic field lines were like concentric circles, right? Now, in the center, the circle will be somewhat like this. For this, it would be somewhat like this. So, at the center, what is happening? The arcs of this big circle would appear straight line. Look, they are almost like a straight line in the center of the circle. Okay, this is the diagram. Next, every point on the wire carrying current would give rise to the magnetic field appearing as a straight line at the center of the loop. Okay, so at the center of the loop, you will see that the field lines are like a straight lines. Okay, now this diagram, I hope it's clear, right? In this diagram, wire was like this. Okay, but in order to understand this diagram, what do you need to do? Keep your wire like this, okay, like this. And suppose the current is flowing up like this. The current from the side that you can see, this side is visible to you, right? The current is moving like this. It's going up, coming down, going up, coming down. How will you decide the direction of magnetic field? Place your thumb in the direction of the current. Current is going like this, and your fingers will go like this. This is how the field lines look, right? You will curve your fingers, and this is how your field lines look. So now if you draw the field lines, they would appear like this. These are your field lines that would appear across the wire. Look, this is the diagram, right? The current is going up. Current is going up. Only this dark part, this dark brown part that has been highlighted in the paper, it is the part that is visible to you. The other part is at the back because the plane of the wire is perpendicular to the surface. Please be very careful with the orientation of the wire. And if you keep your wire like this, these black lines represents the direction of magnetic fields. Okay? And how do we decide? We'll just put our thumb. We'll put our thumb in the direction of the current, right hand, thumb, and curls of the finger gives you the direction of the magnetic field. Okay, so I hope now you're clear with the direction of the magnetic field in both the cases, in this case and in this case. Okay, next, magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Depends upon the current passing through it. We have already studied that B is directly proportional to I, right? Why? How have we decided it? As you increase the current, the deflection also increases, right? Next, therefore, if there is a circular coil having n number of turns, see in this case, in our present case, we just had one turn, right? Now, suppose I have lot of turns. This is like a spiral and I have n turns, right? 1, 2, 3, 4, 5, 6, so on and so forth. I have n turns. So, because of one turn, my magnetic field was B. Due to second turn, it would be B, B, B. And the direction of the field due to all the turns will be same, right? Direction of the field lines or the direction of the field due to each turn will be same. So, they will add up, right? Therefore, it is if there is a circular coil having n turns. N turns means n circular loops like this. The field produced is n times. Why? As large as produced by a single turn. See, because of one turn I was getting B. Because of 2 turns I will get 2B. Because of 3 turns I will get 3B. So, because of n turns I will get n times of B. All the field lines are adding up and they are giving us n times of B. Okay.